A few years ago, I had the opportunity to present at a conference, and unfortunately, I couldn't attend the conference. So what I did is I basically recorded audio using PowerPoint as the mechanism. And this lecture is basically going to be that conference presentation. Unfortunately, the audio quality is pretty poor. It's an example of a really bad design, for lack of a better word. So it's unclear how you'll receive the content. I obviously thought it was important enough to place it at the end of this course, and you'll see some interesting things going on with the audio, not the least of which is some of it was actually recorded at the shore. So enjoy. Hello, I'd like to thank everyone for attending today's presentation. My name is Walt, and the topic is Systems Practices for Sustainability. When people are asked to get together and think and talk about sustainability, they all obviously have different views and opinions of what they think sustainability is. We all seem to know what it is. It's like the sky. The sky is blue, grass is green, trees are green, and so on. The Brundtland Commission actually provided a very succinct definition, which I always offer to different people when I present at these kinds of forums. Basically, it meets the needs of the present without compromising the ability of future generations to meet their own needs. It's obvious. People should live as best as they possibly can without destroying their futures. What may not be obvious is some people think that sustainability is new. I disagree with that. Sustainability is something that we've always practiced. Without it, we wouldn't have gotten to the point where we are right now as a society, as a people on this planet. The issue is we have our technologies, we have us, all the people on this planet, and we have our systems. We see that our systems are being stressed and that there are challenges surfacing in the not-too-distant future. Well, we just need to rise to the occasion. We have to address these challenges and start building our new future. So we have different people starting to approach these challenges from their perspectives. We have product-driven people. Essentially, they feel that they can develop a product that is in a particular niche of sustainability and it will address significant issues in that particular niche. We have technology-driven people. They feel that some form of magic technology can solve many of our sustainability challenges. Then we have financial-driven people who feel that tax incentives, virtual markets will spur innovation, let business rise to the occasion of all of these different sustainability needs. Although I respect what these people are doing, and obviously it's needed, I don't think that they will succeed. I believe that this is a systems problem, and only us systems engineers can actually come in here and bring all of this stuff together and really start to chip away at this problem, not only in a credible fashion, but in a way where we can actually rise to the occasion and address this need. The problem is, who's going to do the systems engineering? That's the challenge. Assuming there are entities that actually surface and are able to start to address the sustainability challenges from a systems perspective, what would be the first step? What would we systems engineers do? In my particular case, I think what we should do is we should take a look at our systems practices and see which ones apply to different aspects of sustainability. I also think that these practices, although they were created for other systems in the previous century, they may need to be modified for systems in this new century. What practices would we select, and how would they be modified? We've all seen the V diagram, and we've used it to represent different aspects of systems engineering. This is probably the most popular version of the V diagram for systems engineering. Basically shows how we get from concept of operations down to implementation. We do decomposition from top down, and then we integrate from the bottom up, and we show our test and integration program going up on the right hand side until we get to validation. This is what we do today. If we were to go off and start to think about sustainability and the new systems, how would we modify this V diagram? What would we do? Typically, the V diagram, for many of us, stops at systems verification. For some of us, we continue on and we show what happens with system validation. Few, however, address the whole issue of operations, years, decades of operations. the implications of that, and then what's involved with shutdown and disposal. As soon as we add that one particular aspect to the V diagram, what happens on the left-hand side? It's interesting because the military has been addressing some of these issues at their local bases for the better part of 10 years. RAND performed a study in which they talked about their sustainability plans, integrated sustainability plans. Would we have something associated with community sustainability of any system that's fielded out there, wherever it happens to be? What would that community sustainability plan look like? Would it be similar to the ISPs that have been developed in the past few years at these different military bases? Would it take on other aspects? What would be the content of this sustainability, community sustainability document? And then, of course, there's this whole issue of how does the left-hand side relate to the right-hand side? We used to use traceability. Is this link a traceability link? Is it an accountability link? What are the implications of that accountability? This is a starting point. It's a proposal. Proposed content includes stakeholders and practices. Who are the stakeholders? What are their needs? What are the key sustainability issues in this system? What are the sustainability goals in this system? What are the key sustainability and stakeholder requirements? What is the accountability path for poor sustainability? The content also includes the practices. What are sustainable requirements? What are the technologies? What kind of technology assessment has been performed? What are the issues associated with innovation, stability? What about modeling and prototyping? Maintainability, logistics, safety, reliability, quality? Should they be started to be addressed in this community sustainability plan? What are the life cycle costs? Architecture identification, trade-off selection? Should the plan just say you should have these practices implemented when you go down this path? Or should it actually start to postulate some of the content, the results of preliminary work in these practices? A suggestion is to model this document after the concept of operations. Fundamentally, the concept of operations tries to capture from the subject matter experts how they think the system should operate. This is a similar thing. The subject matter experts in this particular case are the community, and it should capture their needs from their perspective relative to sustainability. One of the more fundamental and most common systems practices is requirements. We try to identify our requirements. We talk to our stakeholders, we look at similar systems, we postulate what could possibly be with the new system, and we try to identify our requirements. In this particular case, we should be identifying what kind of requirements are associated with sustainability and the new systems that will be addressing these areas. Typically, we would perform vendor searches, literature searches, we would assess different vendor alternatives, and so on. We try to find the discriminators between these various offerings. The discriminators become new requirement categories. For example, in a wind farm, what is the minimum useful wind speed with a particular implementation, with a particular product, with a particular approach? What is the watts per footprint area, linear height, unit of weight? Are these important requirements? Surfacing these requirements, both functional and performance requirements, is not going to be an easy thing to do. Try to visualize what may have happened almost 100 years ago when the amplifier was first created. In the beginning, people just sort of focused in on the ability of the amplifier to just amplify a signal. No one was really interested in frequency response. No one was interested in power output. Distortion and other issues were irrelevant. Those things came later as people started to understand amplifiers, what was important to the stakeholders, and how the different approaches started to discriminate against each other. People tried to qualify them. The same thing's going to have to happen with these new systems moving forward in this new century. Today, I think that's a significant challenge. Part of the reason is most people, when they think in terms of a solution, they think in terms of a system, they immediately focus in on the money. They try to understand how much it's going to cost, they try to understand how much money is flowing through the thing, rather than stepping back and trying to understand, is this function really needed? If we're going to offer this function, what is its performance? What performance should we even extract in terms of measurement? What are the metrics that we need to gather as we identify these different functional characteristics of this system? Some people have suggested that we try to understand the amount of carbon that's used in a system. Alternatively, we try to understand the amount of energy associated with the system. However, in either of those cases, it's more than just the amount of carbon or energy that's used to produce the system or to operate the system. There are also issues associated with packaging and transport. So stepping back for a moment, if we take a look at a refrigerator, it takes a certain amount of energy, or it's going to use a certain amount of carbon to produce it. The refrigerator will have a life cycle of 10, 15, 20 years. And during its life, it will consume more energy or carbon than was used to produce it. If we take a look at a computer, we actually have the opposite relationship occurring. Because of technology movement, computers tend to become obsolete very quickly. Within 2 to 3, 5 years maximum, a computer has outlived its useful life and people essentially get rid of it. And so the computer uses a lot less energy than the amount of energy that's used to produce it. The same thing goes with the carbon footprint. However, that's not the total story. There's also carbon associated with transporting these goods and services across the planet. There's also carbon associated with packaging these goods and services across the planet. And there are issues, for example, where we have very large packages for very small devices, whether it be, for example, 3 screws inside of a package or a box of cereal where the package is extremely small. So all of a sudden, not only do we have total counts or quantities of something that we want to measure, but we also have key ratios that are extremely important. The key ratios need to be identified, and they also need to be compared. 2 of the key ratios shown on this slide are packaging relative to content and transport relative to content. Obviously, there are other ratios that need to be surfaced and need to be understood. And in fact, there's a bigger issue, and that is the issue of how do we actually even begin to measure this stuff. Also, should we even attempt to measure these different items? In recent years, many of us who've been developing systems have been outside of technology development. We've basically been integrating commercial off-the-shelf equipment. In the past, systems were developed from a different perspective. There was actually technology that needed to be developed, and there were these various ad hoc methods that were created. Sometime in the 80s, NASA actually tried to identify these different ad hoc methods and put together a roadmap to perform technology assessment. We also are familiar with previous work by folks such as Rogers, where they talked about technology maturity levels. In this particular case, I think we need to return back to some of these technology assessment, innovation, and stability issues, because these new systems will require new forms of technology. Yes, there are COTS products out there, but are these COTS products really up to the challenge for the new systems that we need in this century? Now, one of the things that we do as systems engineers is we're able to step back and we're able to develop a conceptual view, a conceptual model of an ideal system. When we sit down and we start to identify this ideal system, we identify the functional requirements, the performance requirements. Then we go and try to determine how to physically implement this conceptual system, this architecture. And as the two are blended together, that's where the technology assessment needs to occur. Are these physical devices, products, implementations able to meet our ideal system vision? Now we have a choice. We can either start to drop off from our ideal system vision, or we can start to essentially put in practices, mechanisms to try to foster the movement of these physical devices to meet our system challenge. In other words, expand the technology, expand their performance capabilities. Whatever's involved in making these devices fit into our more ideal system vision. I remember the first energy crisis when it occurred in the 70s. I remember the gas lines. I also remember how people tried to deal with some of these issues. One of the things that many people attempted to do is identify what they could do in their homes to reduce their costs of heating. So there were programs put in place and people started to insulate their homes. Other people went down a different path, or an additional path, of actually putting in passive solar heating systems to augment their solar heaters. The thing that always bothered me is I saw these systems placed on people's roofs, and they were not elegant implementations. After a while, you would see physical sagging of the structures. It was obvious that there was something not quite right. You would see calcium deposits around the tubing. And the point is that, yes, there was technology to augment hot water heating in the home. It was not implemented as effectively as it could have been. And so slowly, as the years have clicked by, people removed these systems and never replaced them. One could argue that this is a quality issue, but it also is a technology issue. Had folks who were developing these systems spent a little bit of time trying to understand the technologies, how it's fitting into the system, yes, quality and maintainability would have been addressed, but perhaps different paths, different approaches would have been chosen once implementing, for example, passive solar heating systems. As part of technology assessment, modeling and prototyping is extremely important. We can use our models and our prototypes to evaluate different architectures and technologies. These are two examples of modeling and prototyping activities. Homer is a software model. It's used to try to understand how different alternative energy systems operate in a system. Various metrics are gathered once the model is executed and offered to the analyst. The Solar System Test and Engineering site is used to test different solar technologies and materials. The trick is to perform this modeling and prototyping activity from a systems perspective. And that's not an easy thing to do. Obviously, these kinds of tools can either be misused or they can be underutilized. The information may not flow out to where the information actually needs to flow out, where decisions are being made, where architectures are being converted into implementation approaches. So this is actually a big issue. What is going on with the modeling and prototyping activities throughout the country? How are these different results being evaluated? Who's looking at this data? And is it being appropriately used once it comes time to create various systems? Prototyping of the solar heating systems, the passive solar hot water heating systems that were offered in the early 70s, would have quickly identified some of the deficiencies of these implementation approaches. Had they been subjected to what we consider to be normal systems practices, such as stress testing, environmental stress testing, and so on, these different issues would have surfaced and they could have been addressed. The result is a more robust system could have been developed, probably for the same costs. The success of a system is not in the initial sale. It's not even in the initial operation. The success of a system is, does the system get used year after year, decade after decade, but more importantly is, once it comes time to have it replaced, is it really replaced or is the system abandoned? That's the true measure of a successful system. Successful systems always get replaced. They are never abandoned. Modeling and prototyping is one of the ways to try to harden these different systems architectures so that they can last beyond anyone's expectations. This naturally leads us to maintainability, logistics, safety, reliability, quality control. Many of us lose sight of the fact that current systems are extremely maintainable, supportable, safe, reliable, and of high quality. And that's because our current systems actually are generations in development. Many times They've had multiple technology infusions. They are successful systems. New systems, especially those based on displacement technology, do not have the luxury of decades of evolution. So all of a sudden, issues associated with maintainability, supportability, safety, reliability, high quality, they're extremely important. So how do you take systems that have been evolving for 40, 50, 100 years and move in new technologies with these new systems that only have 5 years in which to be matured, honed, and developed so that they offer the same characteristics of these other systems that have been around for 100 years? What do you do? This is a challenge. This is where I think systems engineering can add a great deal to the equation. Through the decades, we've developed various techniques for understanding the maintainability, supportability, safety, reliability, and quality of a system. We have all these different practices. Yes, some of them are informal, some of them are formal, some of them are qualitative, some of them are quantitative, but we can go into each of these areas, take a system, understand it from these different areas, and identify where there are issues, where there are needs, and we can make systems better, especially once we talk about new systems using displacement technology. Using these practices on these new systems will actually allow us to try to approach the levels of maturity of the old systems that we're trying to replace. It would be tragic if we succumb to politics and, for example, we put in huge infrastructure systems such as offshore wind power systems, only to find that 10, 15, perhaps 20 years down the line, the system becomes abandoned because of various issues associated with just dealing with salt fog, or maintenance in an ocean environment, or ability to withstand unusual storm conditions. It's nice if there's political will to do something, such as, again, build an offshore wind power generation station, but again, if it's not done properly, it will be lost to future generations. Today there's a renewed interest in sustainability, in energy efficiency. Some of the interest that existed back in the 70s is back again, and there's a new awareness. For example, when we take a look at life cycle costs, waste is now an issue. Shutdown and decommissioning is an issue. Disposal is an issue. These have always been issues, but now all of a sudden people are actually starting to understand that the true cost of a system is more than just the original research, development, production, operation, maintenance. However, there still is the fundamental issue of who pays for these indirect costs. Who pays if the costs get shifted, the burden gets shifted from one area to another area? Again, this is where systems engineers can rise to the occasion and start to surface these issues. There's nothing more egregious than having one stakeholder shift costs to another stakeholder and the other stakeholder not being aware of those issues, of those facts. At some point, the real fun of systems engineering starts, and we start to come up with different architecture alternatives. And as we identify these architecture alternatives, the process eventually starts to surface different trade-off criteria. So what would be the sustainability trade-off criteria? This is a potential list. Air, land, water, sea, space, outer atmosphere, environmental impact. Water, land, air, noise, visual pollution. Fuel and carbon sustainability, internal, external sustainability, regeneration. I haven't spoken much about internal and external sustainability. Internal sustainability is the ability of the system on its own to be sustainable. In other words, to survive years and decades of operation. External sustainability is the impact that the system has on the community. That's what we tend to view when we talk about sustainability. But when we think about the community and the sustainability of the community, it's also very important to understand that the system itself, if it has value, it also needs to survive. It also needs to be sustainable. And that's where this whole aspect of internal and external sustainability is identified. In the past, Most people have said that there's a trade-off between internal and external sustainability. I believe they both need to be addressed simultaneously. It should not be an either-or proposition. It has to be both. And then there's this other aspect of regeneration, the idea of putting a system out there and it actually makes things better. It improves the environment. It either increases biodiversity, it actually cleans the air, or it actually cleans the water. So that's another aspect of a system that can be considered in trade-off. The whole idea of cost shifting to other stakeholders, especially if they're not aware of it, technology maturity, stability, growth potential, model results, what's the maintainability, producibility, supportability, quality of one system versus another system. What about aesthetics? People are very concerned about wind farms being placed in their neighborhoods. Can we do something to make these things aesthetically appealing to the community? Maybe they do have a legitimate complaint. Maybe we should bring in artists into the equation. Maybe we should bring in industrial designers. Maybe there's a way to actually create a beautiful wind farm where stakeholders will actually want this in their community. So this is the traditional aesthetics, form, user acceptability issue that surfaces. And then, of course, we have the traditional sustainability issues of population growth, standard of living, social mobility, quality of life, happiness, survivability. Many people tend to feel that, again, this is an either-or proposition. You have to weigh one against the other. I come from a different perspective. We're systems people, we're technology people, we're extremely creative, innovative. Let's do all of this simultaneously. Is there? No, not is there. There is a solution set that will allow all of these things to happen. We just need to find it. So again, these are possible trade-off criteria to consider as we come up with our different architecture alternatives addressing sustainability. How do we represent our sustainable architectures? Are there generic diagrams that we can use to represent these different alternatives? This is an example of power generation and vehicle use. In some way, this is like a Sankey diagram. We see that we have fatter lines suggesting that more resources are provided or more resources are used. We see that there's some commonality between power and vehicles. Power is electrical energy. We also see that we have electric vehicles. There are alternative fuels, sources of power, and then there are different stakeholders. We have people in houses, we have retail, we have offices, we have industry, we have and so on. We also see that there's also storage capabilities. This architecture depiction actually shows two separate architectures, one for power, one for vehicles. And again, there appears to be many common elements. Notice what ties all these subsystems together is one thin line labeled distribution, and yet that distribution is extremely complex. In the case of electricity, it's wires everywhere. In the case of oil, it's piping and service stations everywhere. So it's interesting how one line can tie all of these things together and yet have enormous complexity associated with it. In this architecture depiction, we see that there's a connection made between power and electric vehicles. The idea is that we may have a large fleet of electric vehicles which can be used to store power, and they can offer the power when needed. In this way, they become part of a broader system picture in which we manage our energy. Is this a reasonable architecture? Is this appropriate? We really don't know. Obviously, many people have suggested this is a way we should go. We should be doing models, we should be doing prototypes, and trying to understand whether this will happen, whether this can happen, whether this is a reasonable approach. Time will tell if the system will evolve and whether it will survive and have the test of time and longevity. Again, there are different lines here. There are different widths. They represent potential flow. One can visualize attaching numbers to these different lines that represent percentage of the total usage. There can easily be notes added to this diagram identifying issues associated with different subsystems, issues associated with the architecture. Obviously, there are other ways to depict this architecture. Again, this is a Sankey diagram approach. Obviously, each of these blocks have different alternatives. They can be depicted in their own way. In this case, let's take a look at storage. When we talk about energy storage, many people talk about batteries, other people talk about flywheels. There's this idea of pumped storage, a reverse dam for lack of a better word. Basically, you have two reservoirs. You fill one side of the reservoir when you're generating energy. When you need the energy, you basically drain the reservoir down. So you're using the height of water to essentially store energy. So yes, each of these blocks have different alternatives, and they'll have different depictions associated with them. So this architecture depiction is the depiction of storage. How are we going to store our different energy alternatives, in this particular case, electric energy? At some point, we actually have different architecture alternatives available. We have requirements, we have models, we even have different cost analysis available. There's initial costs, life cycle costs. We know our indirect costs. We know our direct costs. We understand how much costs are being shifted to possible unwitting stakeholders. In other words, we have an understanding of our different architecture approaches. How do we select the best architecture? A proposed approach is to basically take our trade-off criteria, whether they're weighted or not weighted, really doesn't matter, and sum the trade-off criteria so you have a total rating for each architecture approach, and then divide it by the total life cycle costs. This is, for lack of better words, an architecture measure of effectiveness, an MOE. It's a measure of goodness for each architecture approach. In other words, what is the biggest bang you're going to get for each dollar spent for each architecture approach? Once this matrix is developed and the MOE is calculated for each architecture approach, sensitivity analysis can be performed. Different criteria can have different weights attributed to the different criteria. Certain criteria can be zeroed out of the equation completely to determine what happens in terms of the selection as the criteria come and go from the total equation. This process of identifying the criteria, summing the criteria, dividing it by the life cycle costs, yes, it does lead to a number, a measure of effectiveness, but this process forces the team to defend their favorite architecture approaches. In the process of this defense, massive amounts of information surface. The team truly starts to understand all of the different architecture approaches, and eventually a consensus starts to form. The consensus is based on logic, on reason, and analysis data, some of which is qualitative, some of which is quantitative in nature. But it's a reasoned approach to selecting the best architecture alternative. Cost is then factored into the decision process, but it's the total cost. It's the life cycle cost. It's not the cost of one particular stakeholder. Something as trivial as a context diagram is really not all that trivial. Identifying our external interfaces is extremely important. In this particular case, we're trying to show a city and its external interfaces. Is bad waste really external to this city, or should it be within the boundary of this context diagram? Should all cities be forced to deal with their bad waste, or does it make sense for the bad waste to go off to some other city? There's imports, there's exports. Should that be part of the equation when we talk about sustainability? Recyclable waste, same issue. Should it be within this context diagram? Is it a good thing to send recyclable waste over to other cities? In any case, this is a context diagram. It's one of many possible context diagrams as we address our new cities in this new century and the new systems.